In this project, we're going to be talking about the elements of the periodic table. I will start off talking about the alkaline earth metals and the alkaline metals. Yusuf will talk about the metalloids and the transition metals. Ryan will talk about the halogens and noble gases, while finally Anas will talk about the lanthanides and the actinides. There are 7 main energy levels and 4 sub-main energy levels. The 4 sub-main energy levels are S, P, D, and F. And we should know that one chamber can hold 2 electrons. S has 1 chamber, P has 3 chambers, D has 5 chambers, and F has 7 chambers. That means that the S can hold 2 electrons, the P can hold 6 electrons, the D can hold 10 electrons, and the 7 can hold 14 electrons. The off-pole law states that electrons tend to occupy the lowest energy level. This is the lowest energy level, while this is the highest energy level. The arrows show the lowest until the highest. The alkaline earth metals and the alkaline metals are located on the S block in groups 1 and 2. Alkaline is in group 1, while the alkaline earth metals is in group 2. We can see the information here in the table. We can see that alkaline metals are really reactive, while the alkaline earth metals are also reactive, but less than the alkaline metals. There are also other information like the boiling points of them. While the alkaline metals are low, the alkaline earth metals are a bit higher than the alkaline metals. Start with electron configuration based on the Off-pole law: 1s2, 2s2, 2p6, and finally 3s2. We see that it is in period 3, block S, and group 2. Here we have period 3 right here, and it's in the S block, and it's in number 2. That means it's located right over here. Do another quick example. Here we'll do the off-pole law with the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Now we know that it is in period 4, group 1, and in block S, as shown here. So period 4, 1, 2, 3, 4, group 1, block S. That means it's located right here, the first one.
I'm Yusuf, and we're gonna talk about transitional metals versus metalloids. Okay, we know that transitional metals are metals that are shiny, metallic, and they have luster, and their physical states are solid. Okay, they are good conductors of electricity and heat. Their reactivity, they are very reactive. Like they are known to be very reactive, and the boiling points are high. We know that they are in the D block. The transitional metals are in the D block, and when we're moving throughout the period, it gets less reactive metals. That's what we know about that's why they're called transitional metals, because the transition gets less reactive throughout the D block in the periodic table. Then we have the metalloids. Metalloids are in this zigzag line in the periodic table. This periodic table is called the zigzag line. It includes the metalloids. They are semi-metals. They are not fully metals and not fully non-metals. They have some of the non-metals and some of the metals. That's why we classify them as semiconductors. They are solid at room temperatures, like most metals. The only metal that is not solid in room temperature is mercury. It's the only one that is liquid. The reactivity depends on conditions, so not all metalloids are reactive. They are brittle and easy to break, not like most metals. That's like a non-metal property. They are semiconductors, and their example is like silicon chips. We can use it to be as a semiconductor. And we're gonna use the idea of the electron configuration to find the properties and the location in the periodic table. So we know that silicon 14, based on the off-pole law that Kevin stated, 1s2, 2s2, 2p6, 3s2, 3p2. So we know it's gonna be in period 3. because the highest main energy level is 3, and it's in we know that it's in a B block, so it will pass through the S and D. That's 12, and we're gonna add the 12 to the 2 of the P, so it's gonna be in group 14. So the group number is 14, and we know it's gonna be in block B because that was the last one filled. So when we do this, here is 14, group 14, and here is period 3. So it's gonna be here, silicon 14. And we know based on the table here, it's a metalloid. So it's a semiconductor. It has some properties of metal and some of non-metals. We're gonna use the example also of titanium to find its location using electron configuration. So we're gonna do the electron configuration that Kevin said based on the Aufbau law. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So we know it's gonna be in period 4 because the d is led by a period. The D is always late by a period. And we know because it's in the D, so it passed through the 2 from the S, these 2 from the S. So we're gonna add 2 plus 2, that will be 4. So it's gonna be in group 4. And we know it's gonna be in block D. Okay, so we're gonna go to period 4, which is right here. And we're gonna go to group 4, which is right here. So it's gonna be right here. And based on the map that we see, it's a transitional metal. So it's a metal that is reactive, and it has the properties, it gets weaker when it moves, not the element itself. The elements in the periodic table gets weaker when it moves because it's a transitional metal.
Hi, I'm Ryan. Now we're going to talk about halogens. Halogens are nonmetals that are found in group 17, which is this one. They're also highly reactive nonmetals that form salts and acids. And as they go down the group, their physical property changes and the state changes from gas to liquid to solids. Now we're going to talk about noble gases. Noble gases are found in group 18, which is this one. And they're called stable because they don't easily react to other elements, and they're also called odorless gases because you can't see or smell them, and they also have low boiling points and melting points. Now let's take this example, Cl17. First, let's find the electron configuration for this, which is 1s2, 2s2, 2p6, 3s2, and 3p5. Now let's find the group, which is 5 plus 12 because it's in block P, so this equals 17. So group equals 17, P equals 3 because it's right here, it's the biggest one, and block equals P because this is the last one. So 17. So we have to go 17 units here, just here, and period P, which is this one. So it ends up here.
Hi, I am Anas, and now we're going to be explaining the F block. We now move to the F block, which includes the last two rows at the bottom of the periodic table. They are placed down there because if shown in their real position, the periodic table would be too wide. In reality, they belong between group 2 and 3, which are here, and period 6 and 7, also here. The F block contains two types of elements, lanthanides and actinides. Let's explore their properties. Lanthanides. Elements from atomic number 57 to 71. They are silvery white, soft metals, good conductors, quite reactive, especially with air and water. So they're quite reactive, not fully reactive. Density ranges from moderate to high, so by increasing they get higher in density. High melting and boiling point. Can resist easily oxidized. To form oxidize their chemical properties. When they react with water, they form hydroxide and hydrogen gas. When they react with oxygen, They form oxidized. When they react with acids, they form salts. Now we move on to actinides. Elements from atomic number 89 to 103. They also have a silvery and white metal. Very active, other than the lanthanides, especially when finely divided or broken, which results in larger surface area. All actinides are radioactive. Mostly are high dense metals. They tarnish easily in exposed of oxygen and forms oxide. Tarnish here means lose their color. React with hot water and acids to form hydrogen. Very electropositive, which means they lose electrons easily. Heavy ones like uranium and plutonium can undergo nuclear fission, which releases enormous amounts of oxygen, of energy. Their common and their differences. The common characteristics. Both are in F block elements. Both are metallic and silvery in color. Both show contraction. The atom shrinks because the nuclear force increases. Differences. Lanthanides are mostly non-radioactive while actinides are all radioactive. Lanthanides are stable and not easily oxidized. They do oxidize, but they get stable because of the oxide layer. Actinides are unstable and easily oxidized. Lanthanides has similar chemical properties, but actinides have less similar properties. Lanthanides are found in nature, actinides are man-made. So we will follow what we said by an example, doing electron configuration for GD64, but we will do noble gas notation because electron configuration will be long. Xenon, 4F7, 5D1, 6S2. So as we can see, it ends with 4F, so that means it's in lanthanides. Let's discuss its properties. Silvery white metals, soft and good conductors of heat and electricity, quite reactive, especially with air and water, high melting and boiling points, and form oxides when exposed to air. Okay, for our last example, we're gonna do noble gas notation for MP93 with radon. 5F4, 6D1, 7S2. So as we can see, it ends with 5F, which means it's in the antinides. Let's discuss its properties. Silvery white metals as well. Very active, especially when finely divided, which means when broken or exposed to more surface area. All are radioactive, high density and high melting points, tarnish easily in air, and form oxidized. Tarnish means when it loses its color.